All right, 6.4, starting on page 146, we're looking at polar coordinates. Now, polar, kind of like how we have a North Pole and South Pole, means that there's a specific point that things are radiating out from. So in this case, what we're looking at is we're looking at kind of a coordinate system, but instead of looking at a grid, we're looking at radiating circles. Okay. So looking at our first definition, our goal is to plot points with given polar coordinates, so we need to know what polar coordinates are. The polar coordinate system is a plane with a point O called the pole and a ray from O called the polar axis. Each point P is assigned polar coordinates r theta, where r is the distance from O to the point, which is the radius, and theta is the angle whose initial side is the polar axis and whose terminal side is the ray OP. So what does that mean? So it means we have this point O, and we have this ray, which we call the polar axis, and O is called the pole. Okay, and we have another point P, whose distance or whose radius is r, and this angle here is theta. Okay, to compare this to the Cartesian coordinate system, which is what you're used to working with, we could also write it kind of on a Cartesian plane. Here's point P with radius and theta, and this is still O. Our pole is the same as our origin. And in both of these cases, we would label point P as having radius r and angle theta. So the point, instead of having an xy coordinate, we have r theta. P is labeled as r theta. All right, so in example 1, we want to plot the points with the given polar coordinates. So in part A, we have a radius of 2 and an angle of pi over 3. Okay, so if you remember, the angle of pi over 3 is here, and we have a radius of 2. So there would be point P with our angle of pi over 3. Okay, I'm going to graph these bigger in a second. This is just kind of the sketch. Point Q has an angle of 3 pi over 4. Now 3 pi over 4 was here, but my radius is -1. So instead of having a radius of +1, then we have to draw it down here with a radius of -1. So Q is going to be down in quadrant 4. Okay. And then point R with an angle of -45 degrees. Now, -45 degrees means we're going clockwise 45 degrees, R with a radius of 3. Okay, so now I'm going to graph these bigger. Okay, so starting with I'm going to start with my smallest radius. My radius of 1 with Q is here. Q. And then I have a radius of 2, so I'm going to approximate, that was like 1, 2. There's P with a radius of 2. So this is 2 comma pi over 3. This is 1, -1 comma 3 pi over 4. And then lastly, I have the -45 degrees, which is the same angle here. So 2, 3, and here is R with a radius of 3 and an angle of -45 degrees. Notice how even though these are different angles, even if we wrote -45 degrees in radians, it would be -pi over 4. Right? They're different angles. So our next objective is going to be to find all polar coordinates of a single point. Okay, so looking back at example 1, if I wanted to have this point Q written with a radius of 1, then I could have rewritten this as 1 comma, negative pi over 4, right? So we can see that there are multiple ways now to write the location of a point, whereas in the Cartesian coordinate plane, there was only one way to write a point, just x comma y. Now we can have multiple ways of writing a point. So to find all of those polar coordinates for a given point, we want to let P have the coordinate r theta, and any other point is going to have the form, let's draw a picture so we can kind of visualize this. Point P has the coordinate r theta. Well, if I go straight from my polar axis to my radius, that would give me theta. But notice I could go all the way around and then go to the axis, right? So I could add a full rotation to that theta. So what we end up with is that P could be written as r theta, could be written as r theta plus 2 pi, and I could go around as many times as I want, so I could say 2 pi n. So now I'm saying the point has the same coordinates if I go around as many rotations as I want. I could also have that negative radius, okay? But now if I have a negative radius, I have to go around a half rotation. So this is going to be theta plus pi, okay? But then I can go around that half rotation, and I can go around as many rotations as I want after that. So times 2n plus 1. So that's saying I can go around as many rotations as I want plus another half rotation with a negative radius, okay? Now the equivalent of this in degrees, I can say this is r, comma, theta plus 360 degrees n, which is the same as negative r, comma, theta plus 180 degrees times 2n plus 1. So I'm saying I have to go around an extra, if I make my radius negative, I go around an extra half rotation plus as many rotations as I want. Okay, and n is any integer. In particular, the pole has the coordinates 0, comma, theta, where theta can be anything. Looking at example 2, and we're going to write our answer just in radians because it's given in radians. So we want to find all polar coordinates for P, whose coordinates are 3, comma, pi over 3. So using kind of the ideas from above, we can say that P could be written as 3, comma, pi over 3 plus as many rotations as we want, 2 pi n, or we can write it with a negative 3 radius, angle of pi over 3 plus half a rotation, and as many rotations as we want. So what this means is here's pi over 3 with a radius of 3, right? So here's point P, and this angle is pi over 3. But I could go all the way around and then to that angle, or I could go around twice and then to that angle, okay? Or I could go down here to pi over 3 plus pi, and this angle here would be 4 pi over 3. And then I could go around as many times as I want after that. Okay, so that's what that n does. All right, now that we have these two systems, the polar and the rectangular or Cartesian, it'd be nice to know how to convert back and forth between them. So our next goal is to convert between polar and rectangular equations and to graph those equations, okay? So recall from the last section that if I have a vector, something like this, I can decompose that vector into its x and y components, right? Where its y components, let's say this is r theta. So this is theta, and this has a radius r, okay? Its x component is r times cosine of theta, and its y component is r times sine of theta, okay? This is very similar to how we constructed the unit circle. So if I'm looking at the point P, 3 comma 5 pi over 6, which is in polar coordinates, and I want to convert that to rectangular coordinates, I need to recognize that r equals 3, theta equals 5 pi over 6, and that P as x comma y equals r cosine theta comma r sine theta, which is 3 times cosine of 5 pi over 6, comma 3 times sine of 5 pi over 6. So then we get 3 times negative square root of 3 halves from our unit circle, comma 3 times 1 half, which gives us negative 3 times the square root of 3 halves, comma 3 halves. So this would be our point in rectangular coordinates, okay? If I estimate this, it would be approximately, and this would be on a calculator, negative 2.60, comma 1.5. So I can say that this point is approximately here, point P, which we could also have said directly from our polar coordinates. All right, I'm going to leave part Q for you to do, and you can check your answer with me in class. All right, on the next page, looking at example 4, we're converting the opposite way. So if we're given the rectangular coordinates and we want to find the polar coordinates, and for this we need to recall the Pythagorean theorem, which is, if I'm kind of looking at it like this is my angle theta, this would be my radius, my x, and my y. So x squared plus y squared equals r squared, which would give us that r equals the square root of x squared plus y squared. Now we don't have to worry about the plus or minus because since this is a distance, it has to be positive, okay? We also need to remember that if I'm looking for that angle and I'm given the x and y values, then I can find tangent of theta, TOA, so opposite over hypotenuse, equals y over x, and therefore theta equals tangent inverse of y over x. Or we're looking at what angle would give us that proportion y over x. Okay, now tangent theta you can find on the calculator. So let's look at point P, negative 1 comma 1. I'm going to start by graphing this. So if I negative 1, 1 is here. Now already I can tell that this angle here is going to be a multiple of pi over 4 because my coordinates are the same absolute value, right? So if I'm looking for r equals the square root of, using this equation here, negative 1 squared plus 1 squared equals the square root of 1 plus 1 is the square root of 2. So our radius is the square root of 2. And tangent of theta equals y over x. So 1 over negative 1, which is negative 1. Tangent of theta is negative 1 for quadrants 2 and 4. I graphed this wrong. It should be up here, right? Negative 1, positive 1. Sorry about that. Square root of 2. Okay, in quadrants 2 and 4. So in quadrant 2, our angle would be 3 pi over 4. So we have our theta is 3 pi over 4. Okay, so now we have that our point P can be written as square root of 2, comma 3 pi over 4. we need two polar coordinate pairs. So our second polar coordinate pair could be, what if I put P with a radius of negative square root of 2? What would my angle be? And that's the case where my theta is in quadrant 4. So if we're looking at this angle here, it would be 7 pi over 4. So I have radius of negative square root of 2 and theta 7 pi over 4. And there's my second polar coordinate pair. I'll leave part Q for you to practice. Now that we know how to convert points back and forth, let's look at converting an entire equation. Now, what we need in order to convert, so this is in polar, and we'd like to convert it into rectangular form. So what we want, our goal, is to get an r cosine of theta or r sine of theta so that we can convert that into x and y. All right, so looking at the equation, r equals 4 secant of theta. Secant is 1 over cosine, so if I divide both sides by secant of theta, I can rewrite r divided by secant of theta as r cosine of theta equals 4, which means that this is just x equals 4. Now the line x equals 4, here's where x is 4, is just a vertical line. X equals 4. So that means that this is also what the line in polar should look like, and we can verify that on our calculators. So what you want to do is you're going to on your calculator change your settings. So, all right, I adjusted the camera a little bit so that you can see the calculator better. We're going to go into mode, and then down here where it says function, parametric, we want polar. So we've seen before using parametric graphs. Now we're looking at polar graphs. So you want to hit enter, and that just changed the setting. So now to use that setting, we go into y equals, and now instead of having y equals y1, y2, y3, we have r. So we're writing our equations in terms of the radius in polar equations. So we want r equals 4 times secant of theta. Now there's no quick way to type in secant from these buttons, so we can type it as 1 over cosine. So we have 4 times 1 over cosine of theta. Okay, and then when you hit graph, you can see that it is indeed a vertical line, just as our polar coordinates told us. So how we did that on the calculator is we went into mode, and then where it said function, parametric, polar, we want polar. Okay, now in order to graph back in rectangular coordinates, you will have to go back into mode and change it back to function. All right, for example 6, I'm going to let you do this. It's the same process that we just did in example 5, except now instead of going from r cosine of theta to x and r sine of theta to y, you want to substitute x for r cosine of theta and y for r sine of theta. And then just like up here, you want to write your answer r equals something in terms of theta, so r of theta. Our last example is an application involving polar coordinates. So one use of this is for radar. So if a radar detects 2 airplanes at the same altitude and their polar coordinates are 8 miles and 110 degrees and 5 miles and 15 degrees, how far apart are the airplanes? So let's draw a picture. At 15 degrees and 5 miles out, we'll say it's about there. And then 110 degrees and 8 miles out is going to be somewhere, something like that. Okay, just a sketch. Now we want to know how far apart the airplanes are, so I'm going to draw in here the other leg of a triangle. Now we cannot assume that this is a 90-degree triangle, and in fact we can find this angle, because if this is 15 and this is 110, then this angle here is going to be 110 minus 15, which is 95 degrees. So notice it is not a right triangle. So I'm going to draw my triangle here, and I'm going to make it very clear to myself that it is not a right triangle. This is 95 degrees. This was 8 miles, and this was 5 miles, and this is what we're looking for, okay? So we are going to use the law of cosines for this. And if you'll recall, the law of cosines is c squared equals a squared plus b squared. But then you have to do minus 2ab cosine of theta. So I'm looking for x squared equals 8 squared plus 5 squared minus 2 times 8 times 5 times cosine of 95 degrees. So make sure when you're calculating that, your calculator is in degree mode. Okay, so I say that x equals the square root of 64 plus 25 minus 80 cosine of 95 degrees. And I put that into the calculator to find that x is approximately 9.80 miles, because we're talking about how far apart they are. So they're only 9.8 miles apart. All right, so the last thing that I want you to do is make sure you use this box and summarize what you learned from this lesson.